All right, I think we're live. We need to get some like intro music that'll like kind of remind us we're we're good here. Um, Good to see everybody that's listening in. We have a lot to talk about today, so thanks for stopping by. But yeah, as first thing we'll lead off with is Avalanche Go releases. So I think since our last call, we've had two of them actually, Cortina 13 and Cortina 14. So I'll share my screen here and then turn it over to Stephen and Aaron to lead the discussion on those changes.
Yeah, thanks. Yeah, so I think these two releases have kind of been the start of some of our locking changes for the consensus engine and VM interface in Avalanche Go. So we're really making a push to further enable parallel message handling and eventually parallel verification and execution, which I think we'll talk about in a little bit more in detail, at least on the HyperSDK side and things like that. But yeah, at the end of the day, like being able to handle consensus messages concurrently can end up making the network smoother, have things get processed more gracefully, and also have a higher level of throughput. Um, so we're kind of doing a large kind of consensus engine overhaul right now, which is focusing on that locking behavior. And so these two PRs have not really like significantly changed the locking, but have kind of changed where the locks are grabbed in such a way that we can hopefully push them down further and have much more fine-grained locking in the future. So both these releases are very actively working on that.
Yeah,
Uh,
important to note there for folks that maybe aren't or familiar or forgot is like when we're talking about some of these engine changes, these are underlying all virtual machines that are running on Avalanche. So it's not like, oh, like the P chain locking is getting better. The engine changes we're talking about affect any virtual machine running on the primary network or on a subnet. So when we're talking about these things, they're very wide ranging, but also obviously very sensitive, which is why we're spacing them out over a series of different releases to test out their interaction and stability independently. And yeah, I think the first release here Steven's referring to like changed just the APIs, and then now we're starting to get more into the goodies, we'll say.
Yeah, so like the next release, Cortina 14, also changed a lot of health check locking, shutdown locking, startup locking, things like that. And probably in Cortina 15, we'll see some of the core kind of consensus messages changing with what are called like channel messages, so like build block requests, things like that, and the core consensus messages, so like queries, chits, things like that. So we'll start pushing that down. It should be really really exciting. But yeah, the other kind of things to shout out, I think, on the Cortina 14 was we added into Avalanche Go the I think what's it called? Is it called like rotate subnet ownership TX or something along those lines? It's not activated yet,
It's called
and
transfer ownership, subnet ownership TX.
yeah, it's not activated yet, and I think that the ACP, which I think we'll talk about ACPs as well further in the call, is still kind of being workshopped, but it's a fairly standalone suggested change, and I think that this has been pretty requested for all of the like subnet maintainers out there for a while. So
Yeah,
really
I'd
excited
be
to see the
shocked if anyone
conversation around
objects
this.
to this one. Let's put it that way.
Yeah. Yeah, so
Um,
really excited to see the post on that, and I think that a lot of people are excited to see this. And then we also did a pretty major validator set management refactor in 1.10.14, which shouldn't necessarily have too much of an impact on the node yet. But what it's going to enable us to do is further optimize warp verification. So we won't have to apply delegator weights and validator weights for non-tracked subnets, which are subnets the node is not locally tracking for warp verification. And then I think we'll talk a little bit more about some of the pre-ACP discussions around subnet management and things, or subnet validator requirements. But this PR would also be very critical to that effort as well if that gets to the point of implementation. So past that, let me see if there's anything. I think that. Oh, and then the Pebble DB, of course. So it's not currently enabled yet either to be able to run an Avalanche Go node using Pebble DB, but I think we'll probably see that in 1.10.15 as a command line option for the DB type flag as well. So I think that those are the main things I wanted to highlight in
Still
these.
yeah, it's definitely still some
releases,
tuning
but
to
yeah.
do on the Pebble database side. I think we shipped with what were pretty close to the defaults, and based on some learnings we had with HyperSDK, which has been using Pebble now for maybe the last 9 months. And so there's a ton of things to configure here, like how often like data is synced to disk from memory. Like for example, the redhead log, like if you crash and this is greater than 0, like you're going to have data loss. So certain things that are important to kind of tune here. But then also there's a ton of configs that aren't mentioned here, but simple things like the memory table size, write threshold, like there's also like block size configure, like there's everything you could think of. So we're going to start tuning a lot more of that as we tune and test like the Merkle DB some more as well. But yeah, we'll definitely continue to look at that. So yeah, for those that don't know, like Go Level DB, which is what Avalanche Go currently uses, has been put into more or less an archival state, I would say, and not really any active work going on there. And there's definitely some issues with its performance as it gets larger, like as the database gets larger. And so hopefully Pebble, which is very actively maintained, will provide a better experience there until, we can just use Firewood directly. The other one I wanted to call out actually was from 13 to hop around a bit, but is kind of a cool one related to this prefetching logic. So one thing we noticed, and I think Aaron will probably talk about this a bit later, but when you have a Merkle trie to manage the state of a node, let's just say in the blockchain particular use case, usually you separate out like full trie management from just like really fast access to the key values that you need to actually perform block execution. But the problem is you still need to modify the tree structure after you update keys and values. So let's say you have a tree of like a million keys, during block execution, you read, I don't know, 5 keys and modify them. Well, now for every one of those keys, let's assume that they're on different like parts of the tree, you now have to update all the intermediate path, all the nodes on the intermediate path up to the root and pull them from disk, update their hash if they're not cached. And in a very large tree, it's usually unlikely for most things that you're going to have them properly cached. And so what can help a lot with performance is if you are aware of which keys are going to be modified, you can tell the database, hey, go get all the nodes on this path asynchronously so that when it's time to generate the root, everything should already be in memory, which makes the root generation much, much faster. And so this goes into like our ever present quest to entirely pipeline the execution of the block. We already do deferred verification, at least in the HyperSDK. But especially for nodes where there is no deferred verification and no lock contention around the Merkle DB itself, like using this in the block as keys are updated will just be a huge performance boost. So this was great to finally get out there. I think we actually got it out in 12, but there was a missing interface function, and so it couldn't actually be utilized. So this now can be utilized. So this will be something that we'll continue to play around with and definitely incorporate into the virtual machines that are using the Merkle DB. So yeah, anything in the Core side you wanted to call out here, Aaron?
Nothing too much on the Core side to call out. I could talk more about the parallel intermediate node work and kind of a bit more detail of the fetching.
Yeah, I think that may be a good transition here.
I've
Yeah,
got
I'll
the
pull. Yeah, do you have that issue you posted?
Yeah, it's Go Ethereum issue 28266 if you want to pull that up. Otherwise I can send it here too. Yeah, I just sent it here actually.
I'll find it. Oh, here we go. Perfect.
It's a GitHub issue, not PR yet.
Yep.
Yeah.
All right. There you go.
Yeah. So what we observed was that Ethereum charges the same amount for storage reads, regardless of how large the storage tree that you're reading from is. And what this means is that if you have a storage tree with, let's say, one key in it, in which case that storage tree is going to have a single key value pair, and the depth is going to be, it's only actually going to have one intermediate node. That will cost the exact same amount as if you have a storage tree with, let's say, 100 million key value pairs in it, in which case the depth might be around 6 or 7. And doing a single operation would actually read 6 or 7 different intermediate nodes on the way down. And so what we found was that this can have a big impact on performance in exactly the scenario that Patrick was talking about, which is when you modify key value pairs, if you're just reading them, usually there's some separate database where you have an O of 1 lookup. In Ethereum, it's called the snapshot. And then also if you have a path-based data Merkle tree implementation, then you can read them much more quickly as well. In our Merkle DB, you can do this too. But what we found is that when you actually go to modify the nodes, if there's a large number that aren't already pre-warmed in the cache, then you have to read all of those intermediate nodes when it comes time to actually commit and update the tree. And because of the structure of the Merkle tree itself, it can be difficult to parallelize this in a very easy or simple way. So we've come up with a couple of different approaches of how we're going to try and implement this. One of them is fetching in parallel using independent trees. And this is the one that Merkle DB implementation Avalanche Go started to support, called prefetch. And basically what we do here is we just say, okay, we don't actually need to parallelize the internal Merkle view object itself, because anytime we read a key value pair, we're actually going to traverse over all the intermediate nodes to get there. And since we have some in-memory cache, we'll pull all of those nodes into the cache. And at that point, it won't matter that much. The fact that they're not necessarily preloaded in memory in our tray view that we're going to read, as long as they can be accessed quickly, it gives us perfectly good performance. And the other implementation that we've worked on as well is actually trying to fully parallelize it internally to the tree. And so this is where, the recursive structure of the tree can make it relatively difficult to do. And Go Ethereum, the tree structure actually does all of its modifications and updates by taking a copy of the tree node and then updating its parent, and so fully replacing it. And so this means that if you tried to traverse into the tree and do 2 different updates, you could actually replace one or the other and mess up the tree itself. And so it doesn't really lend itself very easily to parallelizing that structure. And it's also not safe for concurrent access externally, so it's not super simple. And so what we've decided to do internally to the tree is to if you have a batch of key value pairs that you want to update, or if you want to prefetch, for example, then what we do is we actually reconstruct those into an internal tree that follows the exact same structure as the tree itself that's either already on disk or partially in memory. And by doing this, what we can do is we can actually parallelize along the way. So if we have, let's say, 16 key value pair updates that are updating, let's say there's a full node in Go Ethereum and there's 16 key value pairs updating children of a tri node at bytes 0 through 16. What you can actually do is you can pass off all of those updates to the same children of the actual node you're applying to, or the original node. And you can split up all of those updates so you can have all of their children and apply it to each individual subtree instead. And what this allows you to do is just parallelize them as you traverse through the tree in order to get the maximum parallelism possible. And so this makes it so we can actually parallelize both the reads, and also with the same strategy, we could also parallelize the put operations. So that's what we're working on now. And we made this issue on Go Ethereum because we obviously maintain a fork core ETH of roughly a fork of Go Ethereum called Core ETH. And so we wanted to contribute this back upstream, as well as to try and get the eyes of the Go Ethereum team on it as well, since it is a relatively sensitive change. And when they make changes to the tri package, we pull them into our code as well. So since this is relatively sensitive, we didn't want to make the change just in our code base, both because that would make continued maintenance very difficult. And also we thought this was an important performance optimization that we wanted to share with the whole Ethereum community if we're able to get it to work. So we have some benchmarks now. If you scroll further down, I linked my diff so far. If anybody's interested in taking a look, you can take a look here. And the next part that we're going to be working on is actually running this on an EC2 instance with a large level DB instance in the middle. So the implementation right now and the way all of these benchmarks work is that we are parallelizing tri reads, but it's reading Tri nodes from an in-memory mock database, and it's mocking the performance overhead of IO8 by just performing a sweep, which is not really realistic at all. Because if you're doing an actual database operation, it's going to be performing random reads on disk, and the bottleneck will end up being how many random reads can you actually perform in parallel before your disk performance starts to suffer. So in order to do that, we have to test this on a database implementation on Level DB or RocksDB or Pebble that is going to have comparable performance to what we'll actually see in production. And so what we're going to do is we're going to construct a Level DB instance with about 500 gigabytes of test data, and then run the same benchmark and see how performance goes then. So after that, we'll get a much better idea of how much performance increase we can get when we're actually performing this on a real disk. And it'll be very, very dependent on the disk performance itself. But super interested to see how these changes go. It was a fairly complicated change to put the batch get operation that constructs the internal tree and then parallelizes based off of the internal nodes. And the batch put operation will be super interesting too. But the way that we're going to use this already in Ethereum, when you're modifying an individual storage tree, at the end of every transaction execution, you actually send all of the keys that you modify off to a prefetcher, which will then start fetching those in the background under the assumption that by the time you commit the block and you're going to need to commit the tree, you will most likely want to actually modify those keys. And so it'll prefetch in the background until the block has been fully executed and it's time to actually commit the tree. So we're going to switch from using that implementation, which currently sequentially fetches those keys, to actually performing one of these parallel strategies. So first, we're going to start out with the prefetcher and try out our different parallel fetching strategies and compare the performance there. And then after that, we'll potentially also try a couple of different strategies of when it does come time to commit, are we better off just doing a batch prefetch before actually performing the commit operation in order to get the most performance out of it and make sure that all of those nodes are in memory before starting to commit? Or if we actually have to implement a batch put operation as well, so it can parallelize both the random reads that you have to perform throughout the database as well as the put operations. And that will take the same approach of making all of those modifications to each individual subtree and then recursing those changes back up. So it's been a super interesting change so far. It'll be fairly complicated. I think there's a little more ways to go, but really excited to contribute this backup stream as well.
Yeah, I mean, to round that out, I think the question many people ask is like, well, why do this? Like, what does it actually accomplish? Like, cool parallelism. And the answer here is stability. So the faster that Tri nodes can be pulled from disk, updated, and the new root can be generated, the shorter the verification time is for a block. Shorter the verification time is for a block usually means everything's better. So when you get a new block over the wire, you can more quickly check that it's valid. When you're handling verification, usually you kind of take on a busy status in the consensus engine. And so you can now respond more quickly. That'll go away with better concurrent handling. The other part, and which is pushing this back into Go Ethereum, is obviously some of the best experts on Go Ethereum's dialect of code are working on Go Ethereum. So, getting reviews from them on some of the ideas are really important, but also it's beneficial to the EVM in general. So when that's the case, we usually try to contribute back. And as we've gotten various security audits on the Subnet EVM and Core ETH, we've always put up issues for anything that's found in those security audits. So this just continues that effort. But yeah, trees run my life, I guess. All right. So next one, let's go into one of the bigger HyperSDK changes, which was. So this was a fun one. I had a lot of fun with it for sure. Here we go. All right. So quick context. You can see all the resolutions here. This has been on my mind for a long time. But quick context is that I'm just going to write this down that I'm talking about. So when we were first working on the HyperSDK, I had always wanted parallel transaction execution. And some of the first iterations of the HyperSDK included it, but did so in a really dumb way. So what I used to do, or what I did before, was as soon as a block was parsed, I would iterate over all the transactions and put them into execution groups. So, looking at conflicting keys and like putting them in a big group and then trying to create together that like put together this like serial plan per like conflicting group. Well, when you do that, you end up like almost always having very few execution groups because like you're looking at the entire part of the block, not like which threads are busy right now. So there were two huge issues. One is this like pre-processing step could take a long time with a lot of transactions because it's a lot of like n squared type iteration to like make sure that the transactions don't conflict. And then secondly, it was super suboptimal in terms of like what could actually be run at different times. Like based on the ordering of where transactions are in the block, you may be able to run them on different threads and not have any particular problem if like the execution of one ends before the other. So during testing before we released the HyperSDK, we looked at the performance and I was like, not good. It's better actually without parallel transactions, which like clearly means that we implemented it like I implemented it really dumb. And so just removed it and instead just added key prefetching. So like basically said, we'll have serial execution and then we'll fetch the keys we need to actually do that execution async ahead of time. And with simple transactions in the HyperSDK, like some of these simple transfers and mints, like actually was pretty good. But as we've gotten deeper into HyperSDK programs, we got issues. So like if a WASM execution even takes, I don't know, like a couple hundred microseconds to compute, and you have 10,000 of them, and you execute those serially, even if the like database lookup is done ahead of time, like your block execution time can very quickly get into an unstable place. Like you don't want your block execution, depending on your block times, this is also very interesting, but like usually try not to go above a couple hundred milliseconds of execution. Rough rule of thumb, in my opinion. And P99 above a couple hundred milliseconds of execution. And you can't do that with meaningful load unless you parallelize the processing of the engine, or like parallelize the processing of these transactions. And so in preparation for putting together like a HyperSDK program DevNet, it became clear that we needed to revisit some of those assumptions. And so we did that, and I'm actually really, really happy with the result, which was that there's kind of a few separate packages here, but I was able to actually implement parallel transaction execution during building and verification, which is basically like if building's fast but verification's slow, you're slow. If building is slow and verification's fast, you're slow. So you need both to be fast to actually like drive meaningful improvements in throughput. So it was important that we could do both. So I implemented this execution package, which I call the executor, which you can actually use for anything. It's arbitrary. Let me see if I can get this to show up so I can link to it, or at least show a bit of it. Here we go. This is actually probably going to be pretty nuanced. Yeah, the code's in there if you want to take a look up the executor. But the idea is pretty much that you can start off a executor run. And when you start that off, you specify, you basically can add things to the executor like tasks. And that task is basically some function that you want to run with the like conflicts. And the conflicts are just specified as arbitrary strings. And so what the executor does is it says, great, what are the edges of my current graph? So like for every conflict key. So let's say, I have a transaction with key A, there's nothing in the graph, great, you can run it. Now I have a transaction with key AB, well, op1 or op0 had A, so A is blocked on 0, B is unblocked, so I have one dependency. As soon as the first transaction finishes, I can invoke the second one because that's its only dependency. And you can imagine you can generalize this to say, okay, what if I had a transaction with ABC? Well, now if assuming that one is still executing, that one has one dependency and it's the transaction ahead of it, and a B has a dependency of the transaction ahead of it, but no dependencies on C. And so this engine basically has a queue or like a number of swim lanes where it can just execute things as soon as they're ready to roll. And then the executor just makes sure that you're never processing conflicting keys at the same time. So this ensures, and people are like, well, why is parallel transaction execution get kind of funky like this? And it's important that execution is still deterministic, even though it's done in parallel. And so to do that, you have to make sure that you're not accessing the same state concurrently. Otherwise, there's non-deterministic changes that could happen, like based on if you execute it one way or I execute it another way. And so you need this kind of very careful tracking of dependencies and execution for it to work. So what this lets you do is, let's say that you have a transaction that goes from A to B, and then a transaction that goes from C to D. They have no conflicts at all. They can both be processed at the same time. So let's just say that they're WAS and blobs, and I don't know, in the worst case, they take like a millisecond to run. Well, your block time is still a millisecond, even though you have 2 milliseconds of execution that you're doing. But the cool thing, the cool ratio is the way that I've implemented it is you can just scale up as a validator of a HyperSDK network to as many cores as you want to. So right now, I think I split it, or like it's configured to like 2 cores or 4 cores. But like if you had a very execution heavy network, you could just as easily bump it up to like 16 cores if you really wanted to, and your state didn't conflict much. So I see you unmuted, Stephen. I'm not sure there's anything you wanted to add to that, which is a very interesting and extremely complicated topic to go from here, for sure. There are a lot of other ways to do what I suggested.
Yeah, I was gonna ask about actually that. I'm interested on if you have considered or thought about if you would ever want to like partially execute some transaction. So like imagine you have some like WASM smart contract where like halfway through it you're going to end up fetching some value, right? But prior to fetching that value, it's fully deterministic and it's not based on that value. So you can actually do that like first half the computation before that value is needed. So like I assume that the way it works is probably the flow is you pass the actual key values into like the operation, like when it starts to execute it, and then it like runs. But like if instead you like passed like value readers that like block on like I'm just interested on like if you've like thought about kind of fine-grained parallelism.
It could
like
get
that.
crazy for sure.
Yeah.
I would say describe my parallelism here as like a very coarse parallelism, at least on the individual transaction level. The conflicts are defined there, and it's never interleaved amongst that individual transaction level. Now, could you like add readers that actually allow you to fully interleave like ops within a transaction? For sure. That'd be super cool to see. And I think with the structure that we have, it's totally possible to do. It gets kind of rough because I don't think this would actually matter. Never mind. But like we do a lot of prefetching of the keys, but you could just as easily wait for the reader to be given to you to do the prefetch. So I think that point is moot, I would say. So yeah, I mean, I think that that's probably the end goal, is like the fully like kind of streamlined thing. I guess my only question becomes, I don't know if there's like some sort of weird adversarial case where you can like somehow get like a bunch of contracts to be run at the same time that use a bunch of memory that like read from each other in like the super lockstep way that actually makes it really slow to pass the locks back and forth. So I guess there's some potential DOSy considerations there, and I'm not sure how to think through those quite yet, because I'd imagine like this kind of passing back and forth is going to be much slower than just running the thing. So I need to think more about that. But yeah, one actually alternative idea I had, kind of on the same note, was instead of thinking about how to kind of stepwise execute the ops, what you could instead do, and this was from a conversation I had with Henry from Penumbra, who's brilliant. But the idea was like, he brought up this point where like parallelism in these blockchains just gives people too many degrees of freedom. So when you have access to a key, at least in the HyperSDK here, you have full access to make any change to that slot. As a result, my optimizations are limited, right? Because I have no idea what you're going to do there. So I cannot in any way try to like co-sequence things there or whatever. And so based on that one phrase, I was like, what if instead like we added even like op types to the database that weren't like a full set or weren't a full like delete of something, but instead were more of like commutative operations so that you could check, just at the end of execution that like even if you had a bunch of things that were sequenced concurrently, that it was just valid at the end, which is pretty nuts. It's like, so imagine a simple case, right? We're the case everyone always talks about is NFT mints, right? Like I want to mint like 100 bajillion NFTs all at once. Like what's the most efficient way to do that on a blockchain, right? In a case where you don't have parallel execution, like everyone lines up. In a case, even sometimes when you have parallel execution, you're touching the same state as everybody else, so you still line up. And so people are like, well, yeah, parallel execution is great, but not for that because it's still contention around the state. So you have to introduce different things to try and like penalize people for putting like contention in the state processing. So like I think Solana added like priority fees like related to a particular contention around state, so that if there's like a lot of contention, that if you access the non-contentious state, you're just good to go, which is actually an interesting way to like price the open cores maybe you have allocated for parallelism, which I think is, they're super happy with it. I think it's an interesting approach as well. But what if you could say, actually, like if you're all minting, that's cool. Like they're just ads. And if you have some way to limit the number of ads that are going to happen so you don't overflow, like frankly, I don't care who goes first because it's going to always lead to the same result. And so other than maybe like, unless you like price some initial reads differently than later reads, you can understand from that perspective, like how you could actually have concurrent access to a single slot. So I'd be more interested in pursuing that angle than trying to like do a full interleaving of these like these blobs.
This reminds me of a conversation I had with Goon probably like 6 years ago now around like on a blockchain, if like you have Alice, Bob, and Charlie, right? And you like have A pays B, B pays C, C pays A, all like one unit. Like, is this valid if A started with no money, right? Because it's like, well, the flow is, it's fine, right? Like, yeah, like A didn't have the 1 unit to pay B, but at the end of the block, they got it back, and it's essentially equivalent to these kind of like chain native like flash loans that some people have dabbled with, and it's it's a similar vibe of like, at the end of the day, like if it all works out, then like does it matter if you break some rules along the way?
He'd actually be like a great guest to have on here because like he's done some like a crazy cryptography stuff. Like he has this great article around ED 25519, like curves and like how you can use them in interesting ways. But I think his point and like major takeaway was, modern computing has benefited greatly by not giving developers too much freedom so that the compiler can do crazy shit behind the scenes. And in blockchains, like there seems to be in this like world of trying to make high performance blockchains that you like think that the best way to do that is instead to just give developers total control so they can like optimize the shit out of their contracts. And it would certainly be nice if instead you could kind of strike a better middle ground where you can achieve that performance, but maybe by doing so, you give them slightly less degrees of freedom to worry about, such that their code can even get faster, as like optimizations are introduced, rather than requiring like some sort of contract upgrade, which is kind of a crazy premise, or it kind of gets away from the point of what we're trying to do here, I think. Yeah, I could talk about this topic for a long time. Like there's a totally different group of thought, which is like instead to do like STM, which is like software transactional memory. I think that's what it is, right? Something like that. I don't know. But the idea is instead you're just like optimistically executing everything concurrently. And then if there's a conflict, you just have to rerun it again after that. So in the worst case, you execute everything twice. So you may say, like, well, why is that a good idea? Like, it seems kind of wasteful. Well, the huge benefit is that the user has to not specify what the keys that they'll touch ahead of time are. So if you're trying to say like, hey, if we have the EVM and we don't want to change, like we want to keep it fully MetaMask compatible, not introduce anything crazy, like how can we make it faster? That's usually the way people are doing it. So I think Monad, for example, is one of these like other chains that's working on optimizing the EVM, and they're all software transactional memory for that reason. But there's a large open debate in this particular vertical, which is like good or bad. So like Aptos and Sui, they're all software transactional memory. Solana is much more like explicit key specification. HyperSDK is explicit key specification. So, if you want to get into that, there's a lot of interesting materials online that I highly recommend you check out.
My main concern with the optimistic concurrency control stuff is just that like you're not able to really charge them for like that additional run, right? Or can you? I guess maybe you can. Definitely makes it hairier.
I think you can, because the second run is always deterministic.
But I mean, is it? I guess like you have
if
to.
One person has to do a second run, everyone's gonna have to do the second run.
That's not necessarily true, though, is it?
But yeah, because
Like
it's
what-
a key. It's based on key, not concurrent execution when you execute another one. It's like
Well,
if
like
the
the
key's
key
been
could
touched
be-
by
so
an
like-
earlier transaction, then you track that it's been touched by an earlier transaction, and that doesn't change based on like when things are executed, I think.
Oh, so even if the first transaction finished executing and you see the updated value at that point, you'll still throw it away.
You have to, yeah.
Fair.
Yeah, I think like the trick there is just to think about the key order connected to the transaction order. And I think we'll come to the conclusion that like any retry has to be retried by everybody. Like there's no way you can get it somehow like trick the later transaction into like somehow not conflicting with an earlier transaction's execution. Like you're optimistically will attempt it later, obviously. But yeah, it falls out that it eventually ends up being deterministic, the result. Otherwise, yeah, then it's totally broken in this context, which I don't believe it is. Yeah, so we can keep going on about this. Maybe we'll have a separate breakout for this. But we got a few more topics to talk about. So next we'll go into another one, warp payload types. So let me pull up that real quick. Aaron, maybe, or Steven, you guys want to talk about this while I pull it up?
Sure, yeah. So we have implemented two different payload types that were originally placed in Subnet EVM as part of integrating Warp into Subnet EVM. And so these two payload types were an addressed call, which was the ability for one contract address within the EVM to call a different contract address on a different chain, specifying both the source chain, source address, the destination chain, destination address, and then some arbitrary byte payload. And then the other one was a simple block hash. So this allowed you to specify that the EVM should be willing to sign any accepted block hash so that it can prove or can create a BLS multi-signature or warp signature over any block hash and send it to any other chain and verify that, yes, this block was in fact signed by the source subnet. And so we started out putting these inside of Subnet EVM and then decided over time that it was going to be better to make two major changes. One was we wanted to put this into Avalanche Go as sort of standardized payloads. And we saw that as we were building this in Subnet EVM at first there and also going to migrate it to the C chain, it was going to be significantly easier to manage this code if we put it into Avalanche Go for any other VM developer, including the HyperSDK or MoveVM or anybody else that wants to use these same payload types if we put them directly in Avalanche Go, as opposed to putting them in Subnet EVM. And then additionally, what we realized was we could actually take a couple of the fields out of the addressed call. We're building a teleporter smart contract on top of Avalanche Warp messaging, which has been a bit confusing for some people in terms of what is Warp versus what is teleporter. And the way that I would describe it is Warp is simply just signatures and verification of those signatures of only the data that you cannot impersonate. And then Teleporter adds its own payload on top in order to add its own additional properties. So we also removed some of the fields from address to call, realizing that we could put them into Teleporter without any sort of loss of functionality whatsoever. And so we actually removed the destination chain ID and destination address as well, because we realized that building Teleporter on top, all that it actually needs to verify is this source address and payload, because the source address, the EVM itself, needs to verify which address called the precompile in order to determine this is the message that needs to be sent. And so this means that Teleporter can actually define its own payload. And now we'll just need to include this destination chain ID and destination address. And then on the recipient side, Teleporter can also verify the destination chain ID and destination address, or even leave it up to another communication layer or Teleporter itself to choose how to implement something like an anycast, where you can call the warp precompile and say, I want to send this arbitrary byte payload. And I want to send this message that it's valid to be delivered to any chain, as opposed to enforcing that there's an optional field for the destination chain ID. And we made this decision both to move into Avalanche Go and to strip these fields out, largely because we've built Warp with the philosophy of trying to have a minimum trusted computing base and then add additional layers as we go up, with minimizing the level of complexity that's going to be at the root layer, just to make it easier and easier to maintain and minimize the chances that we introduce any sort of bugs at the most important layers of the protocol. And if we do have to fix any issues, it's much better for those to be at the top level than for them to be at the bottom. If there were anything that caused us to need to make any sort of breaking changes, it would obviously break anything above that layer. So removing complexity and building out this minimum trusted computing base has been one of the guiding features of how we've built this out. And so this is a reflection of that change. And also moving into Avalanche Go allows people to much more easily import it. So there's been a lot of requests for more information and documentation. And now that we've moved them to Avalanche Go and we've added this README, should be in a much better place for people to play around with it as well.
One often kind of thing that keeps coming up as well is like questions about what is a warp message actually. And so like these are kind of two standard messages that we expect are probably going to be pretty heavily used between subnets in the following months as Warp and Teleporter go live on Subnet EVM and C-Chain. But these aren't necessarily like the only things that people can use. So VMs can still define a fully custom kind of Warp message. But as we introduce more VMs and more subnets go live, like we're expecting that these are probably going to be the first couple of messages that become kind of more popular, and then we'll probably add additional messages over time as they kind of get standardized. So by no means are these two the only two that can ever happen. You're also not required to use a standardized message format, but in order to facilitate a nice communication between subnets, we expect to see kind of some like core standard of messages that are being passed around. So
I'm at least particularly excited about the hash one, and I've fought tooth and nail to make sure this was in this thing. Importantly, because I think there's a misconception as well that like with warp messaging, like for every individual message, you need to send like one warp message across, which, as you may imagine, like every warp verification requires like BLS multi-signature verification. And you're like, well, like love your thing, but like how are you going to like send 10,000 messages to like some chain or something like that? Like that's a lot of verifications. Well, that's where the hash message comes in. So the idea is that you could just actually share like either a block hash if you wanted to, or in my opinion, what I think is cooler is instead to like build a purpose-built tree structure just for relaying hashes of messages. And then the validators, which are just going to be a lot easier to prove on any other chain rather than like a full block payload. And so the idea is like if we can come up with a canonical like hash structure, which our recommendation is the Merkle DB structure, which is also used for Firewood, and we just write one verifier once, and then you can prove any hash was part of that tree at any point in time, and then just basically reference messages on the destination chain. So Teleporter initially uses address call. It's much easier to reason about for developers, and I think that that's the right call. But as we start talking about like, hey, like Teleporter is pretty cool. Like, can we do more of it? Can we do cheaper of it? I think a lot of it will move into the world of hash-based messages, where you can just send a tree of messages in a single multi-signature. This importantly can also amortize the cost. So instead of you having to like pay for the inclusion on the destination or even like the export on the source, you can just like the network, the validators can just say like, well, every 16 blocks, like we'll just sign a root, then you can just go ingest it somewhere else, and like you can have massive like cost amortization around it, which is I think going to be really important for its adoption.
I've really been trying to find a reason to dive into vector commitments and actually like use them in like a real thing. And this is just screaming to be a vector commitment. So yeah, I
this is why we did the binary tree support, dude. We don't need that's our stopgap. We're not going to use the vectors yet.
So I will say, so the major separation here is that this is not a tree that's changing, right? It's a static tree. So like, there's not really a great
you want to optimize
rationale.
the shit out of that one. Yeah.
Well, because if it's a static thing, like your generation of the tree is going to be O of n, your generation of the vector commitment is going to be O of n. Like basically a vector commitment, assuming things are like relatively evenly cost with the constant overhead, which is not true, but whatever. Then like the vector commitment kind of wins out. But for things that are like dynamically updating, then you definitely need like a tree-based structure, because otherwise the vector commitments aren't any fully standalone, not sufficient. But yeah, I mean, if you're just sending a static tree across, then like, oof, give me that vector commitment. Anyways, I really need to dig into it. I was playing around a little bit with some of the vector commitment stuff, but it was pretty. It seems pretty wet paint. I was playing around with it, but
it's the cutting edge.
Yeah.
I see actually one quick question here from Sean Forsyth that I wanted to loop in. I don't know if Kyle, you can like make that show up on the screen or not. Oh, so dope.
Ooh,
all right,
sick.
Covers my face, but that's totally fine. Could you speak to the scalability of the P chain with regards to the proposed usage for Teleporter? I wanted to bring this up because this is a super common misconception about how Teleporter and warp messaging will work on the primary network. Many people have this assumption that Teleporter messages, wherever they come from, really, which are Teleporter, to be clear, are just formatted warp messages. So it's just warp. Have to go through the P chain or like be verified by the P chain or something like that. And like every message sent everywhere, whether it be to the primary network or to another subnet, requires like this connection or like inclusion in the P chain. That's not true. The P chain just has a registry of the keys of the validators that can sign messages for a particular subnet. So when verification happens, all that happens is that you look up the keys, and then you can use that to verify the BLS multi-signature. Per message, no data is included on the P chain. No thing is like invoked on the P chain. So the scalability of Teleporter has nothing to do with the P chain other than people being able to register these keys, which are, I think the public key is 48 bytes, and the proof of possession, I don't know, let's say it's 100 bytes. So it's more of a function of how many signers there are that are registered rather than like a per message verification bottleneck on the P chain. So you should think of the P chain as like one big address book. It's not a message relayer. Now, at some point in the future, it could become a message relayer if people wanted to like somehow guarantee delivery of messages and maybe even penalize people for not posting message signatures. That's super interesting as a usefulness of like data availability of the messages. Maybe the X chain could actually be better used for something like that. But just to be clear, like the scalability of that is unrelated to anything happening on the P chain. Now the C chain, which will be the integration point for Teleporter, the scalability bottleneck will be how many BLS multi-signatures is it going to target to verify per block. And this is why it's interesting to have like a hash-based structure where like you can put many more messages in a single warp message that's being verified. So I think that hopefully that answers your question.
On a little bit more of a practical note, there is still some interaction with the P chain because it's reading those public keys. but there's no actual like like on-chain work done on the p-chain, right? So you can actually make that read completely lock-free on the p-chain side if you wanted to, and so then it's the same cost as doing your DB lookups on the C chain. So that should get priced in on whatever chain you're doing that verification on. So it's not necessarily related to the P chain, but looking up those keys does have some cost that's included in the charge of your transaction. So on the chain you're issuing it. So
yeah. So we're super excited to see more proposals, like different message types and integrations into different subnets. For the most part, the EVM to EVM path is going to be a very paved road. And then the stuff that between the EVM and other virtual machines is where like more work will have to be done. Whereas if you want to interact with the C chain, either you need to implement some sort of message handler on the C chain that can support whatever you're doing, or you need to comply and like be able to produce messages that like the EVM specific handler can read. So those are going to be the two real options, I think, if you want liquidity from the primary network. So I would imagine most people will, like the most interesting use case there, just to quickly summarize it, is going to be, I have a subnet, I want the gas token to be Avalanche. I can just use that as a native token and then have basically teleporter handle without a trusted intermediary that transfers in and out of Avalanche, which is going to be so cool, I think, and like super useful for subnets that are like afraid to launch because they don't want to have their own token or like whatever. It turns it into like a real just scalability solution where it provides its own security. Yeah. But yeah, we're quickly running out of time, and I want to make sure we get to this last topic because I think it's super cool. So the Avalanche Foundation launched Avalanche community proposals. If you haven't had a chance to look at this yet, highly recommend. For the first time, there's like a really open framework and way to actually propose meaningful changes to the structure of the Avalanche network. And so you can read through this on all the different tracks, like the processes for doing so. And, if you read something, you're like, don't like that. Well, there's the meta track. You can always propose changes to the process if you think that they could be improved. But a lot of ideas now have been posted into this step one, which is, hey, I have an idea for how I think Avalanche could be better. Let me kind of litmus test it in the community and see what people think. And so a few people kind of took the lead on starting some conversations, and I chimed in on this one, which was rethinking the requirements for subnet validators. And posted a long proposal called the Path to 100,000 Subnets. I have really appreciated like all the feedback people have shared with it, and if you haven't had a chance to check it out, leave some feedback. I'm collating all the responses now that people have left, and I'm basically going to send like one big message in line, kind of responding in my opinion to the questions. But we'll likely go forward and post like an ACP proposal one, which will then start off like a more official conversation around more the semantics of the thing. But it seems like there's interest in exploring how like the relationship between the primary network and subnets could evolve. And that's really what this proposal was about. But I think it'd be fun to have like a kind of a Twitter space at some point too, like where people can kind of chat about it, some of the ideas with it. But yeah, I mean, in summary, I think that we should, as a community, change how people launch subnets, or at least open the door to people launching subnets differently. And so in a lot of conversations I've had with the community, the feedback that's come back is subnets are interesting, but the cost to get started and the cost to maintain them is pretty high relative to other options that are out there now. And I think this community discussion forum is a great place to talk about these hard open questions, right? Which is, what is the right cost to be able to launch your network? Like what do people expect to get out of it with that? And so I think, we've had a lot of conversations with the community in general, but think that if we loosen the requirement for subnet validators to be primary network validators, there are ways to redesign the P chain in particular that could allow subnets to launch much more cheaply without destabilizing the network. Now, there are tons of open questions on a lot of that, like what are the fees, like what's the implications of like tokenomics and everything like that, which I'm not going to comment on. But I think it's interesting to explore the idea to make it possible for people to do these sort of things. And I talk about this pretty specifically in this proposed rollout with basically a three-phase plan. First one, very minimal, just basically break the requirement that people need to be primary network validators and replace it with a simple bond, which is very similar to like what is required for staking now. Probably doesn't need to be as high, but just keeps the like loose framework the same. Step two is really about redesigning the P chain to support this flow and making it much more efficient to support many more subnet validators. And when you have many more subnet validator support, or like at least capacity to host them, you can decrease the cost, right? Because the cost is usually a mechanism just to deter DOS. And so if the capacity goes up, you can sustain more load. And so the network should be able to support, much more. And then phase three is where it kind of goes. And the second part of phase two is also changing the payment mechanism. So instead of like bonding some large amount of tokens up front, instead, based on like the demand for subnets and subnet validators, you can just basically like kind of more openly bid to be part of the subnet validators on the primary network. Now, the goal is to have that target be super high. And the reason why we can do that is because the P chain and the primary network doesn't actually like verify anything that happens on the subnets, and validators are not assigned to subnets, which is very different than some other protocols that try to do something like this. And so they've taken a very different approach for like shared security is important. For us, shared registry is important. And I would say that that's the important use of the P chain outside of managing the stake and stake weights and rewards, which allow them to have the full security of the network. Lastly is the one where it gets kind of crazy, which is, I think, a really cool idea. And I'm curious to hear people's, more detailed feedback on it. But this also came straight out of subnets talking about what could be better. And the issue a lot of them have, which is like, Avalanche is a place to create new networks. That's like really to bootstrap ecosystems and build your own, your own world. But the problem is that when you're small in the world of blockchain, it can be pretty cheap to attack for an adversary. And so a lot of networks are pretty afraid to do that until they're at some size of ecosystem. And so what this will allow you to do is basically have supporters augment the security of a subnet by locking up some amount of their Avalanche tokens to that subnet. And what this will allow you to do is basically put that up at stake without actually holding the underlying token of the subnet, and then be rewarded in the rewards from that subnet. Now, the reason why you would do that is projects, at least have a value. Everything does. Stocks, projects, tokens, whatever. And it only is up, changes based on the maturity of the process, the project, like its growth, like how widely it's adopted. And you need this sort of secondary security mechanism when you're small to actually be able to hold like meaningful TVL or like grow the network safely. And if you don't have this, either people will grow the network unsafely or they just cap it, which curtails a lot of the growth that people are looking for when they're launching their own ecosystem. So I think this is a really good thing where it's people in the community that are like, yeah, we want to help subnets grow. And then subnets are like, we want help growing. And it's a perfect place, I think, to be in the middle. Now, Stephen, not as big of a fan for this particular one, but I'll let him express his comments later. I want to talk quickly just on one security consideration, which is important, which is the way that this would work is that validators that want to run without the full primary network or validate the primary network would need to rely on something called partial sync mode. This would mean that they only process P chain. Now, the issue when you only process the P chain on the primary network is that you can't actually fully verify the imports into the P chain because you need to understand what's going on the X chain and the C chain to do that. And so with partial sync mode, you're fully at the mercy of the primary network to come to consensus on correct data. Your verification is going to be limited. And so for people that, this is why you can't be a validator when you're in partial sync mode, because you may not have a good idea of what's actually happening on the network and then vote with your impartial information and then start to steer the network the wrong way. And so it's important that if you're a validator on the primary network, that you verify everything. And in partial sync mode, you're not able to do that. And so this is a trade-off really around cost. So if you want to have full verification of the primary network, great. Well, you're going to have to run infrastructure to support that on the X and the C chain, which will drive up the cost of the non-subnet workload. And then for people running subnets, typically they would just want to run their subnet and what the minimal thing is out there. And if you do that, the P chain plus your subnet is pretty minimal, especially because it allows you to process messages from any other subnet, which is a huge benefit. So I think that this walks a very specific line on good trade-offs between a number of different approaches. And I think the feedback that people have shared is, really interesting on what things they think are good, bad about it. And like I said, I'm going to post a response hopefully tonight, going through each one of those point by point. Yeah.
So I think I see a question asking why do step one and then step two?
Can you share that, Kyle? Can you share that Bill one? Yeah, thanks.
Yeah, I don't know if you want to answer this, Patrick, or I could probably chime in as well.
Just swap in. Hi, Steven. Go ahead. Yeah.
Yeah. So I think the way that this is broken up into steps is kind of nice because while at a high level it might seem relatively easy to just do step one, there's a lot of technical work for the client to actually support that correctly. And there is an equal level of work that would have to go from step one into step two. And so I think if we tried to do them both at the same time, it would be a very large change all at once. So I think just getting step one out and kind of getting us away from that primary network requirement is a good first step to kind of get the network in that position. So as an example of something that people might not necessarily think about with this kind of a thing is that right now we heavily use the invariant that subnet validators are a subset of the primary network for, say, the P2P networking. So like in the P2P networking, subnets need to be able to communicate with the subnet validators. And they can do that currently because they're able to communicate with primary network validators, and that's the same group or the subset. So you're able to kind of just get that for free. So in order to just do step one, we'll have to pretty much fully redesign the P2P networking communication or connection management and like validator set gossiping, just to support that, which, that is already kind of a large change, not to mention the P chain internals that have these invariants kind of like baked in. And so we'll have to tweeze it out. So there's a lot of technical work just getting to step one. And then going to step two, where we remove proposal blocks, do like warp messages to ourselves, things like that, is a whole other step. Not to mention that in order to do that, we probably need to have better BLS registration adoption, to kind of like actually fully unlock that, which might mean, a hard deprecation of the legacy transaction formats, to actually force people to register BLS keys. So there's a lot of kind of like, like this is not a full ACP, right? There's a lot of like technical details that aren't really talked about in Patrick's post, that we'll probably have to flesh out. Yeah.
the feedback that we got early on when I did like a very small prelim circulation of this, and I generally advocate for posting directly here because the best way to circle an idea is like just posting it publicly for people to see. But one of the big things there was, at least with structuring this, that we wanted to at least propose something that was implementable in like the relatively short term. But if you just propose like a super incremental thing with absolutely no context, people are like, seems just like okay, let me just phrase it one way, right? Like, let's say that this proposal instead just said, do this bond instead, like, and don't have to do the primary network. I think people would generally be confused, like, that's it? Like, like you're gonna go through all this trouble to like redo everything, and like your whole vision for where it's gonna end up is like a bond instead of being a mainnet validator. And so some really good feedback, at least that I got early on, was you should, at least in loose strokes, paint a picture of what it could be if you start to go down this road. And I think that this proposal encapsulates in loose terms what step 2 and 3 could be, much more loosely than they need to be for an actual implementation, and for the proposal itself to focus just on step 1 implementation. For a number of reasons Stephen's mentioned, which is that there's a lot of technical complexity for what may sound like a simple change. And I'd say this goes into like when you kick off development of something and you operate under like a certain understanding and you design everything around that understanding, like Stephen mentioned, changing that later is much more time consuming than just like what you may imagine doing that from scratch is. For people that aren't as familiar with some of the engineering that goes on with some of this. And I think a stepwise approach is a great way to introduce functionality without like betting the farm on like one massive upgrade that if it goes south, like the network gets into a really bad place, maybe where it's unstable or because like the more features that you add, like the more code you're changing, the usually the higher probability of a bug. So I think like a very methodical approach makes sense, but conveying that whole approach to kind of tie it all together, I think was the real intent there. Yeah. So, yeah. Yeah, so I'd love to have a conversation more about it. I don't think this is the right forum because it's very much like Steve and Aaron and I, and then comments from people, which is not nearly as fun. So I think that we'll go into do something like that later, maybe sometime next week when I post if I post the actual ACP up for people to consider. And then the last thing I wanted to touch on related to this was a lot of people also ask like, well, how did these things actually get ratified, or like what does the process for acceptance look like? Is it just like Patrick says it's good, so it's good? No. So the way that this works is also documented in the README, and it's really important people understand this, I think, because this is an open process and framework. ACPs are adopted when people run clients with their stake. And like if the majority of stake is running that adopted feature, like it will run. And if not, it won't. So the way that voting works here is like people can signal what stake that they have on the proposal and what stake they plan to run with it. So like if you're a big dissenter and you're like, hey, I have a bunch of stake such that if I don't adopt this, like the network, could fork or not continue, probably not going to be activated. I think that there's a lot of tools that we should add to the network layer to better signal this. So I think like Bitcoin has a really cool mechanism where like you can kind of signal in the handshake what features you support. And then once so many people support a feature, it will just activate. Similar to how I think Solana has a similar mechanism for epochs. And so I think that some work should be done to make that clear, because the worst case in this model, right, is you have no idea who wants a feature. And then when that happens, and then you're like, well, I think most people have it, chain split, right? Or just in the case of Avalanche, probably just a full halt. And so so I think I just want to make that clear on the adoption front. Like it's very much an open process, and you participate in the adoption of things based on the software you run. And it's very important to keep that in mind. Yeah, so there were two good questions actually outside of this. I know we're kind of over time, but I just wanted to handle them, take them really quick. I see Ravindra actually has two, I think, really solid ones. So, Kyle, can you bring up the second one, the most recent one from him or her? Is there some point that you think an audit should be done? Yeah, I think as part of this ACP process, there's basically when things are put into an implementable phase, that means they're ready for implementation. And the recommended phase is like where the foundation may consider recommending something for adoption. But during between the implementable and recommended phase, people should propose like an implementation of that change and maybe like a PR or something like that on one of the community, like the clients that actually supports Avalanche. I think it'd be a really good meta track item for someone to propose, maybe yourself, that should say like, hey, the foundation should not consider recommending something unless it's been reviewed by somebody or audited or whatever. Like, could be an option. Now, it's very difficult to do that, but I've seen some like EIPs, for example, get really good attention from the community on like some of the parameter analysis, or at least I think like 1559 was audited or something like that. So it would be an interesting thing to note as maybe I don't know if it'd be required or should in this case, because there is some cost related to it for the proposer of the idea. But you know, as much as things can be security reviewed, they should be. So that'd be my view on it. Yeah. Then the last one, which I think we'll just take really quick, was the other one from Ravindra. If you can go up to the top, I think it's like the second message. It must have been something that was on your mind because it was like the first comment, like right when the stream started. Last year, Kevin spoke about Avalanche rewriting the EVM to include features such as parallel execution, hotspot isolation, etc. Is this an ongoing effort or was it dropped? So one big thing to note, right, is the primary network includes the EVM. Removing that EVM from the primary network, or like just getting rid of it, extremely difficult thing to do. A lot of state there. Almost all the value of Avalanche outside of Avalanche, the token, lives there.
And believe us, we've thought about it. You know,
it could have been another good ACP about how to re-architect that part of it. But long story short, at least in my opinion, the EVM across Avalanche is definitely here to stay. And so anything that's here to stay, you should always be optimizing it. So we're very much working on optimizing it still. The first step towards that is going to be to try and migrate the state trie to the Merkle DB state trie format, which will allow us to use both the Merkle DB and Firewood as drop-ins. This should allow basically the EVM to run and maintain like a smaller state size, but also it means that there'll be a lot less code to maintain within the Avalanche ecosystem itself, and will allow us, like, there's a lot of stuff here. I'm not going to speak for Aaron. I think there's still a lot to figure out, to be honest with you. But long story short, like at least Avalabs is still focused on optimizing the EVM to make it work as well as possible on Avalanche. Cool. Well, I think that's been a long and wide-ranging conversation. A lot of fun. Look forward to chatting with folks about the ACP stuff soon. So thanks again for tuning in. See you.
Thanks, everyone.